Welcome to the first part of the problem-solving session for Chapter 10. Let's begin with question number 1. Here, the following 4 questions, that is all the questions of Part 1 in Chapter 10, really are the last part of Chapter 9. Okay, so this would be in Chapter 9, but I moved it to Chapter 10 so that our Unit 3 could wrap up with collisions and begin Unit 4 with center of mass. So the first question says, find the center of mass of the system which is shown below, where we have 3 discrete masses, in other words, point masses. M1 and M2 are both 1 kilogram, and M3 is 2 kilograms. Now we are shown an XY coordinate system, and we note the position of the masses. We have mass 1 with the coordinates, the X coordinate is 1, the Y coordinate is 0, M2 has an X coordinate of 2 and a Y coordinate of 0, and M3 has an X coordinate of 0 and a Y coordinate of 2. Since these are discrete, or rather point masses, we can very simply use the formula for obtaining the center of mass of discrete masses. X center of mass is equal to the sum of each of the masses times their relative position on the coordinate system divided by the total mass of the system. Okay, so I, in this case, would go from 1 to 3. I goes from 1 to 3, since we have 3 masses to sum. All right, so we begin with M1 times X1, which is 1 meter. Okay, let's just write X1, plus M2 times X2 plus M3 times X3, but we know that this is equal to 0 since there is no X coordinate for M3, and the sum of the masses here is M1 plus M2 plus M3. Now we can insert the numbers. We are told that M1 is 1 kilogram, and we know its position is 1 meter, plus M2 is 1 kilogram. Its position is 2 meters, 2 meters, divided by the sum of the masses. 1 plus 1 plus 2 is 4 kilograms. The unit kilogram is going to cancel here. Let's just extend the page. And so we are left with X center of mass equals 3/4 of the meter. Now let's obtain Y center of mass. Y center of mass equals, here again, the sum of M1 times Y1, which we know is 0, plus the sum M2 times Y2, which it too is 0, plus M3 times Y3 divided by M1 plus M2 plus M3. That gives us, when we substitute all the numbers, 2 kilograms for M3, 2 meters for Y3, 4 kilograms for the sum of the masses, we get Y center of mass is 1 meter. So the center of mass of the system of 3 masses has the coordinates of 3/4 of a meter in X and 1 meter in Y. And if we look over here, 3/4 of a meter in X would be someplace right here, and 1 meter in Y, and sure enough, there is the center of mass of the system. Notice that it does not lie on any one particular mass, but rather considers not only the value of the masses, but their location relative to an origin. Okay, let's look at next question. Here we have a uniform sheet of steel. Now, this word here tells us a lot, believe it or not. The word uniform implies that sigma is constant. What is sigma? Sigma is the area, mass, density. Why area and not line? Well, because this sheet has an area. And so what is appropriate here when we are told that a uniform sheet of steel is shaped below, we know that this sigma, this mass density, which is equal to mass per area, is constant. And therefore, any one of these squares has the same value of sigma. Well, we're told to determine the x and y coordinates of this rather funny shaped piece of steel. Now, what we're going to do as an approach is that we are going to break up this sheet into 3 segments, each of which we will locate its center of mass. So I propose this is segment 1, and you can clearly see the center of mass is located here. So we'll obtain the coordinates of this point. Let's call this this block 1, and you can see that its x coordinate is 10 centimeters, its y coordinate is 25. Good. So it's as though the entire mass of this rectangular sheet is located at this position here. Now what remains to be determined, let's just label this is x1, this is y1. What remains to be determined will of course be m1. However, because we know that the area density is constant and it is the same for all pieces, for the time being we can set m1, notice here m divided by a equals sigma, so we can set m equals sigma times a1. Okay, well what is a1? That's no problem. Look, we have 20 centimeters in length, 10 centimeters in height. That gives us 200 centimeters squared for A1. Next, I propose that we take this block right here, this square in other words. Its mass should be located at the coordinates 5 for x, 5 centimeters, and 15 for y. So we have x2, y2. Its mass, m2, we're going to use the same approach, is sigma times 10 times 10 is 100 centimeters squared, right? 10 by 10. Lastly, let's consider this rectangle right here. And you can see that the center of mass is located right here. What are these coordinates? Well, 15 centimeters for x, 5 centimeters for y, and m3, using the same approach, is sigma times, let's see, 30 by 10 is 300 squared centimeters. Okay, now what are we going to do with this? Well, to get the center of mass in the x direction, we're going to consider that each of these blocks is actually a point mass located at the center of mass of each of these. And so we begin summing m1, okay, sigma times a1, this is m1, let's label that, times x1 and we know what that is. We'll put the numbers in a minute, plus sigma A2, this is of course M2, times X2, plus sigma A3, this is M3, times X3, and we have to divide by M1 plus M2 plus M3. But guess what? That's going to be sigma times A1 plus A2 plus A3. Okay, and look here. We can, although we did not have a value for sigma, and you were probably getting nervous by the fact that we were using it to describe the mass, look what happens here. We're going to end up dividing by sigma. And so to get the center mass, all we need are the areas that we calculated. What was A1? Well, let's see. A1 was 200 square centimeters. So 200 squared centimeter, or centimeter squared, times, what was X1? X1 was 10 centimeters, plus A2, which was 100 centimeters squared, times 5 centimeters, plus, lastly, 300 centimeters squared times 15 centimeters. Oops. And all that gets divided by the sum of the areas. 200 plus 100 plus 300 is 600 square centimeters. And what you can see is that all the units square centimeter are going to cancel, which is nice because we should technically only end up with centimeter since we're finding the location of a point. Well, let's see, we have 2,000 for the first term plus 500 for the second term. Oh, that's centimeter, plus 4,500 for the third term, divided by 600, just 600 since we eliminated the unit. And let's see, what does that give us? We have 2,500 plus 4,500. That's 7,000 divided by 600, and that gives us 11.7 as the location of the center of mass in the x direction. We can repeat the same for y center of mass with all the y coordinates. So that's going to give us, let's see, numerically 200 centimeter squared times 25 centimeters plus 100 centimeters squared times 15 plus 300 centimeters squared times 5 centimeters. Divide the whole thing by 600 centimeters squared. The centimeter squared, all the units of centimeter squared cancel out. And so we're left with 5,000 plus 1,500 plus 1,500 again. Now, is that correct? Let's see. 300 times 15 is or is that 5? No, that's 5. 300 times 5 is 1,500. Yes, I apologize. Centimeters. Divide that by 600, and we get 3,500 divided by 600 gives us 5.83 centimeters as that center of mass. Let me just double check something. Yes. So let's go back up to the diagram. 11.7 and 583 puts us at 11.7 is somewhere over here, and 5, I hope I didn't make a mistake with my calculation. If I did, I hope that you will correct me. So anyway, that takes us to a point someplace over here as the center of mass of the system. If I've made a numerical error, then please make the correction. I've had to plug this into my calculator as I record, and it's entirely possible that I have made an error in the numbers. Okay, next question. Show that the center of mass of the uniform rod of total mass M and total length L lies midway between its ends. Now, I've deleted the calculation here deliberately because I'm going to do it with you, and I'm going to show you step by step how you go about solving problems like this. Okay. The first thing that we want to do, in a sense, is what they've done for us. We want to draw the rod, which is just basically meant to be one-dimensional. In other words, it's not meant to be a rod which is length times width. It's just a very thin rod, or in other words, a line. Okay? Now, the first thing that you want to do, let's write down the formula for obtaining the center of mass. Because this is an infinite sum, in other words, we don't have discrete mass elements here. We have little tiny mass elements dm, and we have so many of them that our sum is deemed to be infinite, and of course that takes us to an integral, which is an infinite sum. So here the position x of every dm, little infinitesimal elements of mass, divided by dm, the sum of the total mass of all the little infinite mass elements. And we are going to begin the sum at x equals 0 because our first little mass element is here, and we're going to end the sum at x equals L, since this rod has a length L, as we are told, and the last little mass element here is that position L. So we are summing all the mass elements multiplied by their respective positions in the numerator, and all the total mass divided by the denominator. This is no different than what we did earlier, except that we consider the infinite sum as well as opposed to the discrete sum. Now, how do we begin to do an infinite sum? The first thing we do is that we randomly select a mass element dm. And the reason that we do that is we want to be able to set up our integral. We're going to say that this element of mass dm is located at position x from the origin, okay? Which is in a sense what we have here already. Now, the second thing that we want to do is that we want, so this is the first, to draw and select your mass element. The second thing that we want to do is to consider the relationship between mass and linear density. If this rod is uniformly distributed in mass throughout, then it should be true that the linear mass density, linear because this is a line, is the ratio of either the total mass to the total length, and because this is a constant number, this ratio is constant and in proportion, it should also be equal to an infinitesimal mass element, dm, of infinitesimally small length dx, as this is right here. So the length of this little piece dm is dx. And what this allows us to do is to re-express dm in terms of lambda times dx. Notice that this is not much different than what we did earlier when we had the sheet. Remember when we had the sheet? Here, let me just put it on the side. To get m1, we took sigma times a1, but in this case it was an area, so we used a sigma, and the same was true for m2, m3, whatnot. This time what we're doing is, the difference is that we have a little infinitesimal dm with a little infinitesimal length dx, and lambda because it's one dimension. Okay, now the third thing that we do is to substitute this expression here into our integral and perform the integration. X center of mass equals, we know we're summing from 0 to L, x, but instead of writing dm, we're going to write lambda dx divided by, here, sum, or integral, lambda dx. Now, because the lambda is constant, remember it's a constant, it's just like a number. The thing is that we are representing it by the letter lambda, but it might be something like lambda might be, for example, 2 kilograms per meter, in other words, mass per length, or it might be 1 kilogram per meter, half a kilogram. Whatever the case is, it's just a number, and therefore it can come right out of this integral. So 0 to L x dx divided by, again, out of the integral, 0 to L dx. Now, notice that the lambdas cancel, and when we perform the integral x dx, we get x squared over 2 from 0 to L divided by x 0 to L. Okay? X squared over 2 becomes L squared over 2, and x becomes just L. So here we have that gets divided by L, let's just say over 1. Well, you can see that this L squared will cancel this L, and we're left with the center of mass located at L over 2, and we have shown what they asked us to do using calculus and the idea of the linear mass density, etc. Now, let's come back over here. Had our lambda not been a constant, if it would have depended on position, if they would have given us some functional form of lambda, for example, lambda as a function of x equal to 3x squared minus x, for example, we would not have been able to pull that out of the integral because this would have been variable. It would have no longer been a constant. And in fact, such is the case with the next problem. Okay, now let's go ahead. Let me go ahead and remove this because now we're going to do this problem. Let me delete this and just move this over. And if you have, I don't know what this crazy symbol is here, and I wouldn't worry about it, but the lambda that's given to us here is alpha x. Now notice that this is a lambda which is a function of x, right? It has a functional form. Alpha is just a number, okay? A constant, a number, 2, 3, 4, 5, whatever the case is. And they say because the mass density is not constant, in other words, the mass distribution is non-uniform, in other words, the linear mass density is variable with position. Now to find the center of mass, we have to set up the integral just as we did before, with the difference being, of course, that alpha cannot be taken out of the integral. So I won't set this up again, but you know what we did. In the first step, we drew. So here is the drawing for us. We know that x center of mass is equal to the infinite sum, which begins at 0, ends at L, x dm, divided by 0 to L dm. Okay, step number 2. Step number 2 here is that alpha, which is equal, lambda, which is equal to alpha x, is equal to dm over dx, which means that dm in this case now is equal to alpha x dx. Now the alpha can come out of the integral, but the x certainly can't. So last step, we now substitute these values in the integral, 0 to L. X times dm becomes alpha x dx. Oops, dx. This is our dm. Okay. Divided by the integral, 0 to L, of dm, which is alpha x dx. Now, let's clean this up a little bit. Alpha is a constant, can come out of the integral. So we're left with 0 to L, x squared dx, divided by, alpha comes out of the integral, 0 to L, x dx. Let's perform the integration. We have, these alphas are going to cancel. So we have the integral of x squared dx gives us x cubed over 3 from 0 to L, divided by x dx integral is x squared over 2 from 0 to L. That gives us L cubed over 3 times, and I'm just going to write the reciprocal here just to make life easy for us, 2 over L squared. So this L cubed cancels 2 of those, and we're left with 2/3 L as the location of the center mass. By the way, in this rod as well as the previous one, Y center of mass was equal to 0, since it was assumed that because it was so thin, it lied entirely along the x-axis. Okay, let's solve the last problem in this segment. Here, question 4 says, show that the center of mass of a right triangle of total mass m, base A, and height b has the components of center of mass x sub m equals 2/3 A and y sub m equals 1/3 B. Okay, now while you have this on your notes, I am going to go ahead and eliminate it because we are going to work this out ourselves. So let me delete this, and let me delete this, and oops, what in the world? Let's delete that. Something happened. Let's delete this. Let's shift this over here, and we'll begin with the first part. We want to show that x center of mass is equal to 2/3 A. In other words, 2/3 along the base of the triangle. Well, we have to set up our integral. That is always the first thing that we want to do so that we can work through the integral. So, well, they've done it for us, but let's go ahead and just repeat what they've done here. We take the right triangle and we place it on the xy plane. So we have, this is y, this is x, oops, y, why did I write 8? This is y, and this is x. There's some angle theta, which we don't really care about. And this time, to get the representative mass element dm, okay, we are going to choose some rectangle. Before, it was it was just a little segment of line. But here, we're going to have dx for the base of this rectangle and y for the height of this rectangle. And this is our dm. Now, this rectangle is located at position x from the origin. So now we have it set up. We remind ourselves that to get the center of mass, we need xdm, and the x's run from 0 to a, right? From 0 to a. And so in other words, we're summing all the rectangles beginning at x equals a all the way to x equals 0 all the way to x equals a. 0 to a dm. Now here we have to, this is our part 2, we have a situation here where we don't use lambda because we now have area. So same as we did with the sheet, we have sigma, which is a constant. It's uniform, which is great because sigma equals total mass over total area, or also the ratio of dm over dA. So what is dA? Well, let's see. dA, the area of this little rectangle, is equal to length dx times height y. So dA is actually equal to, well, it might sound better to say y dx. So let's write this down, dm over y dx. So in other words, rewriting dm equals sigma times y dx. And this gives us a way of handling, being able to put something into our integral. But there's one more thing that we have to do. That is, when we are doing an integral of dx, we have to make sure that any other variable that's put in there, such as y, remember lambda is a constant, can come right out of the integral, but y is not a constant. In fact, you can see that y varies from 0 to b. So we have to find the x dependence on y, in other words. So to do that, let's come over here and note that the slope of this line right here, and generally most lines, is y equals m being the slope. I don't know how we can write this. Let's just write slope so you don't get confused with mass. So slope slope x plus b. b being the y-intercept, in this case is 0. So what is the slope of this line right here? Well, if you take this point right here, this point has the coordinates a, b. This point has the coordinates 0, 0. The slope is delta vertical over delta horizontal. So b minus 0 divided by a minus 0. So our slope is b over a, and we put an x right here. Okay, well, this is a very good thing because now we can come back to, let me extend the page, we can come back to dm and replace what we just obtained for y, and that makes life much simpler for us because now we have everything in terms of x. So dm equals sigma, remember that's constant, b over a times x dx, where this is our y. Now, finally, we can go and set up our integral. X center of mass is equal to 0 to a x dm, here's dm, sigma times b over a x dx. This whole thing is dm, divided by 0 to a dm, again, sigma b over a x dx. Well, you can guess what's going to happen. B and A are both constants. Sigma is a constant. So all these right here, this will come out of the integral, but so will this. And guess what happens when they come out of the integral? They will cancel. And so our integral will look like this. 0 to a x squared dx divided by 0 to a x dx. Much nicer looking integral here. Well, let's see. After we integrate, this gives us x cubed over 3, which gives us, after substitution, a cubed over 3, divided by x squared over 2, which becomes a squared over 2. This a cubed cancels a squared, and this 2 comes to the numerator, this 3 in the denominator, and sure enough, we have demonstrated that the location of the center of mass is 2/3 a. A little more challenging integral, but still quite doable. Now, let's work with y center of mass. So here, let's redraw our triangle so that we can set up our integral. Always to set up your integral, you want to identify the dm that you're going to be summing. Now, in this case, we don't want a vertical rectangle, we want a horizontal rectangle, right? The horizontal rectangle, which has the length dy, and it has, okay, here's how we're going to do this. This dm is located at x from the origin, right? This is our dm right here. This is our dm, our representative mass. And we're going to be summing all of them from y equals 0 to y equals b. Now we know that this is a. So the length of our rectangle here is a minus x. See? When x is equal to 0, it's this bottom one right here of length a. When x is equal to a, it's this top one right here where there would be no width whatsoever to the rectangle. So now that we have this, again, dm is equal to sigma times dy. Okay, so we want to see what we can do here because, oh, sorry, not d, okay, dy times, because it's an area, a minus x. See, this is our dA, right? This is our dA. It's length times width. Okay, again, we want to eliminate the x in favor of the y because now our integral is in y and x has a dependence. Earlier, we found that y is b over a times x from the slope of the line. Solving for x now, we get x is a over b times y. Boy, this is getting easier and easier. So y center of mass is equal to 0 to L, 0 to B. This time it's y dm, or y times sigma dy times, okay, A, let me start a parentheses, A minus X, or in other words, A minus A over B, Y. And we divide by 0 to B, this whole thing, sigma dy times A minus A over B times Y. So what you can see is we're going to have to start a new sheet here because I won't be able to extend the page. Let's see if we can come over here and start a new sheet. There we go. All right, so once again, just to remind you, Y center of mass, we have, when we make our substitution, we have 0 to B, Y, and I'm going to factor out the A from the, so we have, I'm going to pull out sigma right here and factor out the A so that I end up with A times 1 minus Y over B times dy in the numerator, factor out the sigma, 0 to B, Y times, not Y because we don't have Y here, A times 1 minus Y over B dy. Okay, let's see. Well, the sigmas are going to cancel. The A's are going to cancel. So far, so good, because both of those are constant. And so they get factored out of the integral, and both numerator and denominator have these. Now, we are going to take this integral and we're going to distribute it so that we have 0 to B, y times 1 times dy gives us y dy minus integral from 0 to B, y squared over B dy. So effectively what we've done is, because we have a sum of two terms, well, one of them is negative, we've effectively just multiplied through the integral. Here, 0 to B, dy, 1 times dy is dy, minus, here, 0 to B, we have y over B dy. Okay, get the hang of it? All right, let's do these integrals. Lots of calculus here, but it's all very simple integration. The biggest difficulty is with setting up the integral. In other words, selecting the mass elements and looking at the relationships between x and y. Well, the first term will give us, actually, I don't need the integral here. Let me just erase this because we can go ahead and just integrate this quite simply without having to follow the steps. Y squared over 2 from 0 to B minus y cubed over 3b from 0 to b divided by y from 0 to b minus y squared over 2b, this is a 2, from 0 to b. Okay, substitute, we get b squared over 2 minus, we're going to end up with b cubed over b, so this will be b squared over 3 divided by b minus b squared over b gives us b over 2. So this looks a little bit like intermediate algebra at this point. Well, let's see. Let's do common denominator at the top here. Common denominator is 6. So we have 3b squared minus 2b squared over 6 divided by b over 2. Well, that gives us b squared over 6, okay, times the reciprocal here of 2 over b, and that gives us, this b squared cancels that b, 2 gives us 1/3 b over 3 is y-center mass, which is exactly what they wanted us to determine. Well, this concludes the first part of Chapter 10 problem solving session. Until next time.